Hello viewers, today we are going to discuss the concept of second derivative test. Viewers, in our earlier videos we have discussed uh, the first derivative test for determining the maxima and minima of a function. So let us take the second derivative test. Let f be a twice differentiable function on an interval I. Clear? Now let C be a root of the equation f prime of x equal to 0. Clear? Then we conclude that C is a point of local maxima if the value of the second derivative of f at C is less than 0. Clear? This is less than 0. And the second conclusion is C is a point of local minima if f double prime of C is greater than 0. Clear? So viewers, let y equal to fx be a real valued function and let f be a twice differentiable function on an interval I. Let C be the root of the equation f prime of x equal to 0. The critical points are given by equating the first derivative equal to 0. Clear? So we have the critical points by solving the equation dy over dx equal to 0, and let C be one such root of this equation. Then this value C is a local maxima, is a point of local maxima if f of double prime of C is less than 0. It means f double prime C is negative. Then C is a point of local maxima. C is a point of local minima if f of double prime of C is greater than 0. It means f double prime C is positive. Okay? So this will happen if we have a point of maxima, and this will happen if we have a point of minima. Clear? So viewers, in our earlier lecture we have discussed the first derivative test, and now we have the second derivative test. Clear? Now let us illustrate this concept or this algorithm of second derivative test by taking a simple example. Clear? Viewers, now the problem is find all points of local maxima and local minima of the function fx equal to x cube minus 3x plus 3. Now this is a cubic function. Clear? Now the first step is to find its first derivative. Clear? Say if this is y equal to fx, then we'll find dy over dx, and this is equal to 3x square minus 3, and the critical points are given by equating f prime of x equal to 0. Clear? Or here we can also say that for fx to be maximum or minimum, the first derivative must be 0. Clear? So here we have 3x square minus 3 equal to 0, and we have x square, 3x square is equal to 3, so x square is 1, and we have x is equal to plus minus 1. Clear? Okay. Now let us find the second derivative. So the second derivative of fx is given by 6x. Clear? Because the derivative of x square is 2x. So this is 3 2s are 6x, and the derivative of 3 is 0. Now here we will find the value of second derivative at x equal to plus 1. So here we have 6 times of 1, which is 6. So this is greater than 0. This implies that f double prime of 1 is positive. So therefore this x equal to 1 is a point of minima, local minima. This is a point of local minima. Now we have x equal to minus 1. So f double prime of minus 1 is 6 times of minus 1 here. So we have here we'll substitute the value of x. So we have minus 6, which is less than 0. So this implies f double prime of minus 1 is negative. So this point is a point of local maxima. Why? Because the second derivative test states that if the value of the second derivative at the critical point is positive, then that point is a point of local minima. And if the value of second derivative at the critical point is negative, then the given point is a point of local maxima. Okay? So this is how we establish that x equal to plus 1 and x equal to minus 1 are the points of local minima and local maxima respectively. Now let us find the maximum and minimum values of this function. So the minimum value will occur at x equal to 1. So f of 1 is 1 cube. Here we will substitute 3 times of 1, we have plus 3. This is 1 cube is 1 minus 3 plus 3. So this get cancelled. This is 1. So this is the value of local minima, local minimum value. And the local maximum value occurs at x equal to minus 1. So we have minus 1 cube. This is minus 3 times of minus 1 plus 3, and this is minus 1 cube is minus 1. This is minus plus. This is 3. This is 3. 3 plus 3 6. 6 minus 1 5. So this is the value of local maximum. Clear? So this is how we solve this problem. Clear? So here's, let us take one more problem. Now viewers, we have the second problem. Find all points of local maxima and local minima of the function. Here we have the function y equal to fx, is equal to 6x cubed plus 3 by 2x square minus 3x plus 8. So let us first find f prime of x. So dy by dx is given by, this is 18x square. The derivative of x cube is 3x square plus this is 2x and 2 get cancelled, so we have simply 3x, and here we have minus 3. Clear? So this is the value of first derivative, and we can take 3 common here. We have 6x square plus x minus 1. Clear? Now the critical points, the turning points are given by f prime of x equal to 0. So we equate this polynomial to 0. So we have 6x square plus x minus 1 equal to 0. Now we'll factorize it by middle term. So we have 6x square plus 3x minus 2x minus 1 equal to 0. We have 3x times 2x plus 1. Here we have 2x plus 1 equal to 0. So here we have 3x minus 1 and 2x plus 1 equal to 0. So we have x is equal to 1 by 3 and minus half. Clear? Now here we have 2 roots of f prime of x equal to 0. Now let us find the second derivative. So the second derivative is given by this is 18x square, so we have 36x plus 3. Clear? So the second derivative is 36x plus 3. Now let us test the value of the second derivative. So we have f double prime of 1 by 3 is 36 times 1 by 3 plus 3. So this is 3 12s are. So we have 12 plus 3, this is 15. So this is greater than 0. So therefore f double prime of 1 by 3 is positive. Clear? And we conclude that this x equal to 1 by 3 is a point of local minima. Clear? This is a point of local minima. Now let us find the value of second derivative at x equal to minus half. So we have 36 times, this is minus half. Here we will substitute x equal to minus half. So we have plus 3 here. Now this is 2 18s are. So we have minus 18 plus 3, which is equal to minus 15, and this is less than 0. So therefore f double prime of minus half is negative. So therefore by second derivative test, this point is a point of local maxima. Clear? So this is how we find the points of local maxima and local minima. Now viewers, here we can find the value of local maxima and local minima by substituting the value of x in fx. Clear? Okay, so first we'll find f of minus half. So this is the local maximum value. This is the local maximum value. So f of minus half is 6 times minus half cube plus 3 by 2 times of minus half square and this is minus 3 times of minus half plus 8. Clear? And f of 1 by 3 is the value of local minimum. Clear? So this is the local minimum value of the function fx. So this is 6 times. We'll substitute the value x equal to 1 by 3 in this equation, this function. We have cube plus 3 by 2 times of 1 by 3 square minus 3 times of 1 by 3 plus 8. Clear? Now viewers, we'll solve this expression, and we'll solve this expression to get the value of f of minus half and f of 1 by 3. Clear? So viewers, when we calculate the value of f of minus half, we get 73 divided by 8, and when we calculate the value of f of 1 by 3, we get 133 over 18. So this is the local maximum value, and this is the local minimum value. Clear? So viewers, let us take one more example. Now viewers, let us take this third problem. Find all points of local maxima and local minima of the function y equal to fx is equal to this is 2x cube minus 6x square plus 6x plus 5. Clear? Okay. Now we'll find the point of local maxima and local minima by using second derivative test. Clear? So let us solve this problem. Here we have the first derivative is equal to, and this is 3 to the 6x square minus 12x plus 6. Clear? Now for critical points, the first derivative must be 0. Clear? So we have 6x square minus 12x plus 6 equal to 0. Clear? Now we divide it by this equation by 6. We have x square minus 2x plus 1 is equal to 0. So viewers, we have x minus 1 whole square is equal to 0. Clear? Now solving this, we get x is equal to 1. So x is equal to 1 is the only critical point for this function f. Clear? So x is equal to 1 is the only critical point. Now we shall examine this point, which is x equal to 1, for local maxima or for local minima. Clear? So viewers, let us find the second derivative. Now the second derivative is this is 2 6 are 12, 12x, because the derivative of x square is 2x, so 12x minus 12. So here we have 12 times x minus 1. Now the critical point is x equal to 1. So if we substitute here f double prime of 1, we calculate, so we get 1 minus 1, which is 12 times 0. This is equal to 0. So here we see that the second derivative is 0 at x equal to 1. Clear? So here the second derivative test fails, because here the second derivative test is not able to tell us what is the sign of the second derivative at x equal to 1. Clear? So here the second derivative test fails in this case. So we will go back to the first derivative test. So let us apply the first derivative test. Clear? Because in second derivative test we know that if f double prime of c is greater than 0, then it is a point of minima, and if f double prime of c is less than 0, then it is a point of local maxima, and here we have local minima, but here we get 0. So now we will have to go back to the first derivative test. Clear? So viewers, here we have the first derivative of f as 6 times x minus 1 square, and the critical point was x equal to 1. Now we'll test this point x is equal to 1 for local maxima or local minima by using the first derivative test. And what is first derivative test? First derivative test is, if we have x is equal to 1, this is 1, then we'll take 2 points. One is immediate left of 1, which is 1 minus h, and then we take the second point, which is immediate to the right of 1, so this point is 1 plus h, and we'll find the sign of the first derivative at this point and at this point. So let us find. So f prime, that is f dash of 1 minus h, is 6 times, here we will substitute for x equal to 1 minus h, and here we have minus 1, we will substitute x equal to 1 minus h. Clear? So this is square, so here's this is 6 times, 1 and 1 get cancelled, we have minus h square, so we have 6h square. Clear? And h is a positive quantity, so this whole quantity is positive. So we have the sign of the first derivative to the left of x equal to 1 is positive. Clear? Now the sign at this point, that is 1 plus h, is 6 times, we have 1 plus h, and here we have minus 1 square, and we have 6 times 1 and 1 again, we have this here we 1 and minus 1 get cancelled, we get minus h square, here also 1 and 1 get cancelled, and we get h square. So again we have 6h square. This is again positive because h is greater than 0 and the square of any quantity is positive. So this is positive. So here's what we conclude from this discussion. We conclude that the derivative does not change sign. Clear? So this is to the left of 1, the derivative is positive. To the right of x equal to 1, the derivative is again positive. So the derivative does not change sign. Clear? So therefore by first derivative test we conclude that the point x equal to 1 is neither a point of local maxima nor a point of local minima. Clear? And such a point is known as the point of inflection. The point of inflection. Such a point is called point of inflection. And viewers, in my next video I will discuss this concept of point of inflection. So here we see that we have a function, we differentiated it, and for critical points we equated the derivative to 0, the first derivative to 0, and then we get x equal to 1 here, and this is the critical point. And if we apply, and when we have applied the second derivative test, we saw that the second derivative test fails to determine whether this point x equal to 1 is a point of local maxima or local minima. So in such situation we switch over to the first derivative test, and when we have taken 2 points immediate to x equal to 1, one point is to the left and other point to the right, and we obtained the sign of the derivative, we see that in both cases the sign remains the same and it is positive. So the sign does not change. Clear? Hence we say that such a point is neither a point of local maxima nor a point of local minima. Clear? And such a point is known as point of inflection. Clear? Now viewers, I am taking one more problem here, and this problem is a very conceptual problem. Find all points of local maxima and local minima of the function fx equal to x cube. Now viewers, this is a famous function. It is a cubic function, and we know that the graph of this function looks like, we can draw it like this. We can draw it like this. Clear? So this is fx equal to x cube. In our previous classes, while studying functions, we have already come across this function fx equal to x cube, and the domain of this function is the set of all real numbers. Set of all real numbers, and the range is also the set of all real numbers. This function is an odd function because f of minus x is minus x cube, which is equal to minus x cube, and this is equal to minus of fx. So this is an odd function. These are some of the characteristics of this function fx equal to x cube. So the domain is the set of real number, the range is the set of real numbers, and the graph lies in the first and the third quadrant. Clear? Now here we have to find the local maxima and local minima. Clear? So what we will do, we will find the points of local maxima and local minima by using the second derivative test. Clear? So let us find the first derivative. So f prime of x is 3x square. Clear? Now for critical points, we have f prime of x is equal to 0. Clear? So 3x square is equal to 0. So x square is 0 and x is equal to 0. So we have x is equal to 0 as the critical point. Clear? Now let us find the second derivative. So we see that the second derivative is 6x. Now if I calculate the value of the second derivative at x equal to 0, we get 0. So here also the second derivative test fails, and we are not able to tell whether x equal to 0 is a point of local maxima or local minima. So viewers, again we'll go back to the first derivative test. Clear? So let us do it. So here I am writing the critical point here, x is equal to 0, and now we will calculate the sign of the first derivative to the immediate left and right of x equal to 0. So this is x equal to 0. So to the right we have 0 minus h, and here we have 0 plus h. So let us find the value of the derivative at these 2 points. So f prime of 0 minus h is 3 times 0 minus h square. So we have 3 times of h square, and always remember h is greater than 0. So this is always positive. Again we find the sign of the the first derivative at 0 plus h. So we have 3 times 0 plus h square. So we have 3h square again, and this is positive. So here we see that the sign of the first derivative does not change at the values very close to x equal to 0. Clear? So when we move from 0 minus h to 0 plus h through x equal to 0, we see that the sign of the first derivative doesn't change. Hence we conclude that by virtue of first derivative test, we declare that this point x is equal to 0, this is x equal to 0, is a point of inflection. This is a point of inflection. Clear? So here there is no point of local maxima and local minima, but we have this critical point x is equal to 0 as the point of inflection. Clear? Now viewers, I am taking one more conceptual problem, and the problem is find all points of local maxima and local minima of the function fx is equal to x square. In other words, we can also say that find the maximum and minimum values, if any, exists of the function fx given by fx equal to x square. So here we know that this is a quadratic function. This is a quadratic function, and from our previous knowledge we know that this represents an upward parabola. Clear? So here's this function, it looks like this. Clear? So this is how we represent this function. Okay, now this function is even function. This is even function. Why? Because f of minus x is equal to f of x, and the domain of f is the set of all real numbers, but the range of f is only the positive real numbers. Clear? So here's let us find the maximum and minimum value of this function. Clear? So for this we will differentiate this function. So f prime of x is equal to 2x. Okay. Now for critical points we substitute f prime of x equal to 0. So 2x is equal to 0 and x is equal to 0. So this is the critical point here. Okay. Or we can say that this is the turning point of this function, x equal to 0. This is the point. Now if we find the the second derivative of f, we get 2, and this is always a positive quantity, because f double prime of 0, if we put x equal to 0 here, we'll get 2 only. So this is positive and greater than 0. So therefore by second derivative test we know that if the second derivative is greater than 0, then C is a point of local minima. Clear? So here x is equal to 0 is a point of local minima. And the local minimum value of the function is can be calculated by substituting x equal to 0 in fx equal to x square. So it is 0 square, so this is 0. So this is the minimum value. This is the minimum value. Clear? Now what about the maximum value? We have already calculated, or we have already claimed that x is equal to 0 is the critical point or the turning point here, and x equal to 0 is the point of local minima, and the local minimum value is f of 0, which is 0 square equal to 0, and this is the minimum value. So what about the maximum value? Clear? So here's from the graph we see that the maximum value or the point of maxima, there is no point of maxima, or we can say that from the graph of the function f has no maximum value, and hence no point of maximum value of f in the set of real numbers. Okay? Because in both sides the graph will get extended up to infinity. As the value of x increases, as x increases, then fx also increases. So here, whatever be the value of x, whether it is positive or negative, we get a positive value of fx. So the graph will rise up to infinity in both the directions here. So we conclude that f has no maximum value, and hence no point of maximum value of f in R. So the only point of local minima is, or the minimum value of f is 0, and it occurs at x equal to 0. Clear? But here I would like to sorry, I would like to mention one important thing, that if we restrict this function, or the domain of this function then we can find out the maximum value. Okay, suppose here if f is defined, in the interval say -4 to say 4, or say 3. So here we have, say this is 1, this is 2, this is 3, this is 4. So this is -4, and here we have 1, 2 and 3. And if the function is defined between these 2 points, or we restrict the domain in the interval -4 to 3, then the maximum value occurs at -4, x equal to -4, and f of -4 is 4 square, it is minus of 4 square. This is minus of 4 square, so this is 16. So this is the maximum value. This is the maximum value, and the maximum value occurs at x equal to -4. So this is how we explain the concept of local maxima and local minima with respect to this function. So here's once again I am repeating, this function is extended as x increases. So these two branches will get extended up to infinity. Hence, from the graph we conclude that there is no maximum value of f, and hence no point of maximum value of f in the set of real numbers. Clear? Now viewers, I am once again taking a very conceptual and important problem, and here we have to find the maximum and minimum values of f or fx, if any, and the function given here is known as the modulus function or the absolute value function. Clear? So here we'll first draw the graph of this function, and from our previous knowledge of functions, we know that the graph of this function, it looks like this. This is so we have the graph of absolute value like this. Clear? So viewers, here this part is known as y equal to, or say if this is function y equal to fx, then this is y equal to x line, and this line is y is equal to -x. Clear? This function also lies in first and second quadrant. Clear? The domain, or the domain of this function is the set of all real numbers, but the range of fx is only the positive real numbers, including 0. Clear? So this function is defined as, this is a piecewise function, and it is defined as fx is equal to x if x is greater than or equal to 0, or we can say it here x greater than 0, and this is 0 if x is 0, and fx is -x if x is less than 0. Okay, so this is how we define this absolute value function. Now we are interested in finding out the maximum and minimum values of this function. So here's from the graph we see that the function f, the function f has a minimum value 0. Clear? So the minimum value occurs at this point. Clear? So the minimum value occurs at or maximum value of f is minimum value of f is 0, and it occurs at x equal to 0. Clear? And from the graph it is very clear that f has no maximum value, because these two parts of this function, they can be extended up to infinity as the value of x increases. Clear? So the graph clearly shows that f has no maximum value in the set of real numbers, and hence no point of maximum value in the set of real numbers. Clear? So viewers, here we can find the maximum value if we restrict the domain of this function, absolute value function. So if we restrict the domain, say if we restrict the domain of f to say -4 to 3, say this is -1, this is -2, this is -3, this is -4, and here we have 1, 2, 3, 4 like this. And if we restrict the domain of this function f to this interval only, then f will have a maximum value, and the maximum value will occur at x equal to -4, and at x equal to -4, and the maximum value of f is mod of -4, which is equal to 4. So this is the maximum value in this case. Clear? So viewers, in today's lecture we have discussed the concept of second derivative test, and we have solved some problems based on second derivative test. Then we discussed the cubic function fx equal to x cube. Then we discussed fx equal to x square, and then we discussed fx is equal to mod of x. Viewers, all these functions are very conceptual functions. When we study these functions in relation to some other concepts, then we can deduce important results. Clear? So viewers, in our next lecture we will solve some more problems on maxima and minima. Thank you.